Going to do the evaluation of an integral that is a little bit complicated, but it's doable. So we have this integral from negative infinity to infinity of cos x dx over x squared plus 1. So we are going to use complex analysis to solve this. So using complex analysis. So when we are using complex analysis, so we use Euler formula. So using Euler's formula. Remember, complex z is equals to x plus I y. And the Euler formula is x is equals to cos x plus I sine x. So this is the real part. So this one is the real part. So remember, we are interested in the real part of that. So let's substitute the Euler inside the equation. When we substitute it, we are going to say the integral of minus infinity to infinity of cos x z over z squared plus 1 dz. That's what we are now having. So remember, we need the real part. The real part. So we need the real part. So we will say the real part of the integral from negative infinity to infinity of e to the power I z all over z squared plus 1 dz, the real part of that. Why we say that is because if you look at this part here, is this part here, which is associated with this one, the real part. So this is the real part, which is actually this one. Remember, it came from this part here. So if we put, for example, we say E I Z is equals to cos z plus I sine z. I'm giving it as an example for you to see, but it's not the big deal. The big deal is we need the real part. So this is the real part, and the real part was there before, but it was in terms of z. But this is the real part, which we substitute to there. So if you understand that, that's better. So we are going to use the contour integration. The contour integration involves, for example, if you are going to have the Cartesian plane there, so if I have I here, and I'll have negative I there, so this will be a pole, and this is a pole, and the contours form around the pole. These are the contours around the pole. So this is the pole. Also, this is the pole. So we will then go to the idea that leads to the Cauchy's residue theorem. Cauchy residue theorem. Now, what does Cauchy residue theory state? It states that the integral around a contour of f of z dz is equals to 2 pi I, the sum of the residues of f and z of k, where k is a 1 to n. So this is the theory for Cauchy residue theory. So we are going to use the residue theorem. So definitely, what is he saying? He is saying if you integrate, so this is integrate a contour, about the contour, this is a contour, in a closed plane, closed loop, that's a closed loop, right, of a complex function. Complex function is 2 pi I is a constant, is the sum. So it's the sum of all residues about the poles. That is what he's saying. So looking back at our integration, now you have to look at the denominator. I have got the positive I and the negative I. So it means that if I have got my Cartesian plane, that is a complex plane, that has got a real part here and an imaginary part here. So I am integrating here from negative infinity to positive infinity. So I am going this way, negative infinity to positive infinity. I'm going this way. Then definitely my contour in the positive side is going to be like this. So I'll definitely go like this to form my contour. And you see I have the positive I here and my negative I is at the bottom. And you can actually say, let's define like I'm coming from the negative R, real, to positive R, where R approaches infinity. So I will go like this. This is the direction. And then make a contour like this. So this is the pole I'm interested with. The pole. This one is out of the contour. Out of contours. So when it's out of contour, it means it's not wanted. So I am interested with the one inside the pole. So as long as we can find the poles, we can find the residue. So let's apply our Cauchy theorem. It's Cauchy residue theorem. Let's apply the Cauchy's residue theorem. Right? We are basically saying the integral, I'll write it in a simple form, of f of z c dz. I'm not going to write it completely, but I'll write it in a simple form because I'll be rushing to do the work. The theory, I'm done with it, of residues like this. So I'll just leave it like that. Then what does this now state? It means that my 2 pi I, and I've got one pole. So this one, it's one pole, it's one pole. So I cannot sum one pole, I'll just use one pole. So what does that mean? And it's in the positive sector. So it means that it's going to be the limit as z approaches to I of what? Z minus I E I Z all over xz plus I z minus I. Like now, to help those who don't understand where this is coming from, I will help you here by actually putting clear the definition, right? What we say is, for single pole, like you see, I had a single pole. It's actually limit as Z approaches Z naught. That is the pole Z minus Z naught of f of Z, right? Remember, my Z naught is equals to I. So definitely I will write it as equals to 2 pi I. The 2 pi is there. Then I come here, limit as Z approaches my I, you see? Then I will put this Z minus I multiplied by the function. The function which I had before was E I Z all over the Z plus I, the Z minus I, and close it like this. So I guess you understand. So there is no cheating. So you cancel here. You can actually see, you can cancel there. So we are going to have 2 pi I, the limit as Z approaches to I of EIZ all over Z plus I. So we take limits where there is a Z. You put in an I there. So what we are going to have is a 2 pi I bracket E I to the power 2 over I plus I. So I'm helping those who might have problem to see their mathematics, because I like showing everything. I squared over 2I. But you know that in I squared is equals to -1. So we are going to have a 2 pi e to the power -1 divided by 2I. Or I left another I here. So this 2 will cancel. This I will cancel. So we'll end up having a pi e -1. That is the answer. Is a pi over e. That is our solution. Please, this one is an advanced mathematics. You find it in calculus, complex analysis at university level, mathematics or physics, higher levels. And yeah, if you like my video, please subscribe for more. I'm going to put more complex mathematics and complex physics, including quantum physics and relativity and tensor calculus. So you're going to see a lot on my channel very soon. Subscribe and look forward for more. Ask questions or ask anything. I'll be pleased to answer you anytime. Thank you.